Hello everyone, my name is Po-Wei. Today I'm going to present lightweight contextual logical structure recovery, a work done by myself, Abhinav Ramesh Kashyap, Dr. Yan Xiaoqin, Yajing Yang, and Associate Professor Min Yang Chen at the National University of Singapore. Logical structure recovery in scientific articles associates text with the semantic section of the article. We categorize each text into one of 23 predefined categories of the logical structures, such as the title, author, affiliation, email, section header, and body text, etc., each of which indicates the hierarchy of the document structure. Previous work have done so by integrating rich text features, spatial layouts, and visual cues, which begs the question, can we obtain state-of-the-art, or at least near state-of-the-art performance on logical structure recovery without relying on feature-rich information, but on context only? Our data consists of the sec-labeled dataset created by Liu Wang in 2010, and is a mixture of computer science papers on computational linguistics, natural language processing, and human-computer interaction. We split this dataset not by line, but by document to form the training, validation, and testing dataset in order to account for cross-line context. We also add more recent ACL papers for testing purposes and an additional much larger unlabeled dataset that we use in semi-supervised learning. Apart from the continuous nature of the document text, the categories are actually quite skewed in terms of the occurrences, which increases model biases towards the majority classes. In order to account for context in neighboring text, we add an additional layer of sliding window attention within the sentence embedding generation and the linear classification layers. What this does is that it pulls the embeddings from neighboring sentences into the target sentence embedding, and greatly resolves inaccuracies of the model prediction within the block of text that relies within the same logical structure. To generate more accurate sentence embeddings, we further fine-tune pre-trained transform models to do so. We obtain the sentence embedding by three methods. The first one is to use a classification token. Second one is to take the mean pooling of the tokens by averaging them. And the third one is to take the attention pooling by inserting an extra self-attention layer that pulls all the tokens into one single embedding. In addition to architectural modifications, we tackle the lack of labeled data in SDP by utilizing semi-supervised learning and data augmentation in order to make use of the abundant unlabeled data. We employ easy data augmentation, which augments the text on a word-by-word basis, and back translation, which generates paraphrases of the input text. We employ unsupervised data augmentation, UDA for short, as one of the two semi-supervised learning frameworks in our paper. UDA adds an additional consistency loss term that measures the robustness of the model predictions by taking the divergence of the unlabeled data and its paraphrase version. We also employ fixed match, which generates pseudo-labels on weakly augmented unlabeled text and uses that to compute a cross-entropy loss on the strongly augmented version. Although semi-supervised learning can help with performance, it doesn't do so on the minority classes, instead amplifying predictions on the majority classes. So what we do is to attempt to emphasize training on the minority classes by employing loss engineering techniques that were seen in semi-supervised learning. One of them, training signal annealing, was originally introduced in unsupervised data augmentation to reduce overfitting on labeled data, but we found that it has the capability to emphasize training on minority classes. What it does is that it imposes a moving confidence ceiling on model predictions, and only those less than the confidence ceiling is computed into the loss function. We also introduced a version of UDA that is supervised, where we add an extra consistency loss but on labeled data. So we don't require the large amount of unlabeled data and reduce computational costs to achieve a more streamlined and lightweight logical structure recovery model. In terms of text-only performances, we are able to increase performance on the macro F1 scale by 7% by considering contextual data, and an extra 3% by adding the loss engineering techniques. We also found that semi-supervised learning does seem to increase the robustness of the model on documents not similar to the training data. Furthermore, with such techniques, we're able to achieve similar results on the model that relies on rich text information for inference. Thank you for listening.